In this video, I'm going to go over the questions from the first review for Chapter 6. So we're going to look at some exponential word problems and then some graphing of exponential functions. So this first one is talking about a town has a population of 9,000 people and grows at 3% every year. So I'm going to first set up my formula using the amount at time t, so in this case, after how many years, equals the initial amount times, I'm going to use 1 plus the rate raised to the power of t. And the reason I chose addition in the parentheses is because I see that word grows, right? So I know it's going to be getting larger. So I'll leave this as a at time t equals 9,000 is my initial amount times 1 plus 0.03. Remember to write that as a decimal raised to the power of t. So at this point, I have my equation for my exponential function. So I just need to plug in this 9 where it says t to figure out what my answer is for the population of this town after 9 years. Now, if you wanted to, you could put the 1 and the 0.03 together to be 1.03. It's up to you. You don't have to. It's your choice. At this point, I'm going to go to my calculator. So here's my calculator to type in this right here. So I'm going to type in 9,000 times 1 plus 0.03 raised to the power of 9. So approximately 11,742, and it says to round to the nearest whole number because we're talking about people. So I'm going to round this to 43. So 11,743 people. All right, so that is it for the first one. Now, the second one is a very similar problem. I'm going to use the same basic formula here, or my initial value. Now, this time I'm going to choose subtraction in between because it says decays. So that means this element is going to lose mass. So 1 minus our rate raised to the power of t. All right, so the beginning mass is 140 grams times 1 minus 0.216 raised to the power of t. And this is per minute, and it's asking for after 20 minutes. So I'm going to be plugging in 20 where it says t. Again, like before, if you wanted to do 1 minus 0.216 to get 0.784, you totally could. All right, that's fine. You can do that. But I'm going to go ahead and just leave it like this and go straight to my calculator to type. So 140 times 1 minus 0.216 raised to the power of 20. Let's see what the rounding is to the nearest tenth of a gram. So the nearest tenth, here's the tenths place. So I need to go to the number after it in the hundredth place. So that 7 is going to round this 0 to be a 1. So 1.1 will be how many grams is left. So it's getting pretty close to being gone. All right, so that's number 2. All right, let's do number 3. Number 3 is switching to investments. This is actually the next link. And you'll see in 3 and 4, it's a little bit different depending on how they're compounding. I chose this one because this one says compounding continuously. So when it says compounded continuously, this is a very special case. And you're going to be using a base of e, right? So you can do the amount at time t equals, we're going to say p. You can also use that lowercase a. It's the principal times e raised to the rate times time. So the rate and the time are both in the exponent. So in this case, I'm going to have the initial value that they invested is 77,000. Wow, that's a lot of money. Times e raised to my rate, which is 0.046, and then times t. Now we want to see how much money would be in the account if we don't do any more depositing or any withdrawing after 12 years. So I'm going to evaluate this at 12 years. Make sure when you do this that the 12 and the 0.046 are being multiplied and that they're in the exponent. All right, so I have 77,000 times e raised to 0.046 times 12. So if Isaac doesn't do anything with the account after he deposits $77,000 into it, compounding continuously in 12 years, he'll have 133,727, and we're rounding to the nearest cent. So we'll have $133,727, and this number here is 0 is not going to change the 7, so 0.67 cents. So this is my answer for number 3. Now, number 4 is very similar, but we're compounding, in this case, monthly. So I'm actually going to use another formula, kind of a variation on the first formula I used in 1 and 2. So you'll notice it's a little bit different. So we still have that A, the initial amount, but this time I'm going to put the rate over the number of times you're compounding raised to the number of times you're compounding times t. So this is another one that you'll need to make sure that you know the difference depending on how they're compounding. So let's plug in what we know. Peyton is investing $690, 1 plus the rate of 0.056 over compounding monthly, which is 12 times, raised to the 12 times t. Now, if you wanted to, like I said before, you can go ahead and do 0.056 divided by 12, then add that to 1 if you wanted to simplify first. But I just go ahead and plug in how many years we're doing here, which is 8. And again, this is assuming Peyton does not touch the money in terms of taking it out or depositing more, which is probably not what most people do. All right, so I'm going to evaluate this at 8, and I'm rounding to the nearest $10. So go to my calculator to type this in. So I have $690 times 1 plus, let's get a fraction here, 0.056 over 12, and then raised to the 12 times 8 power. So to the nearest $10 means I need to go to the ones place, which is this 8, which is going to round this to be $1,080. So 1,000. Oop, that's not where that goes. $1,080. All right. So that's it for the investing. I have 2 questions where I wanted to go over how to graph these exponential functions. So remember, to find the asymptote, you're always going to look to see what is this number after the exponential component. And what you should notice is this 1/2 is between 0 and 1, right? 0.5 is between 0 and 1. So this is going to be exponential decay. So it's going to be decreasing the whole time. And my my asymptote is y equals 1. So you'll notice here is my asymptote at y equals 1. If I plot some points here, I have -7, +9, -6, +5, -5, +3, and then -4, +2. You'll notice when I draw this, it's going to be decreasing the entire time from left to right. So this is exponential decay. Make sure when you draw it, try not to cross that asymptote. So this is the first one here, number 5. Now, this next one is going to be exponential growth. You notice that my base is greater than 1, so this is going to be increasing the entire time. Again, focusing on this value after the exponential piece. So my asymptote is y equals -5. So you'll see my asymptote here, right? And then for the graphing the points, I'm going to do -2, -4, -1, -3, 0, -1, and 1, +3. You could probably squeeze on there 2, 11, or -3, -4.5, but you don't need to. We're going to be increasing the whole time from left to right. All right, don't forget to put those arrows on at the end. And this is the graphing of exponential functions. So don't forget, you can find the links for both of these from these sections. These questions are from 6.1 and 6.2. You can practice those and make sure you're ready for the test. Good luck.